Welcome to Podcast Learn and Fun. Let's start today's journey of learning.
Okay, sounds good.
Have you ever gotten stuck when you're trying to solve an integral, like you just hit a wall?
Oh yeah, definitely. I know what you mean. It's like you can stare at it forever and you just can't figure out what to do.
Yeah, exactly. So what can we do in that situation?
Well, there's a technique called integration by parts. Have you heard of that?
Integration by parts. Is that like where you break the integral into smaller pieces?
It's kind of like that. Yeah, you're breaking it down, but it's more about rearranging it to make it solvable.
Okay, so how does that work?
It's actually based on the product rule for differentiation, which tells us how to differentiate two functions that are multiplied together.
Okay, I vaguely remember the product rule from calculus class.
Yeah, right. Well, integration by parts kind of reverses the process.
So you're saying we can use the product rule, but in reverse to solve integrals?
Exactly. We can rearrange the product rule and integrate both sides to get a formula for solving integrals.
So we're kind of trading one integral for a different one.
Yeah, and the hope is that the new integral is easier to solve than the original one.
Okay, so how do we decide which parts to choose? Like what to rearrange?
Well, there's a handy mnemonic called LIATE that can help.
A LIATE, what's that stand for?
It stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential.
Oh, okay, I see. But how does that help?
So LIATE helps us prioritize which part of the integral to label as u, which is the part we differentiate.
So if we have an integral with a logarithm and an exponential, we should pick the logarithm as u.
Exactly. Because the derivative of a logarithm is usually simpler, it makes the whole thing easier to solve.
Okay, that makes sense. So can you walk me through an example?
Sure. Let's take the integral of x times e to the power of x.
Okay.
So following LIATE, we would choose x as our u because it's an algebraic function.
Right.
And we would choose e to the power of x times dx as our dv because it's an exponential function.
Okay, so then what?
Then we need to find do and v.
And how do we do that?
So do is the derivative of u, which is just dx in this case.
Okay.
And v is the integral of dv, which is just e to the power of x.
Okay, I'm following so far. So we have our u, do, v, and dv. What's next?
Now we just plug these pieces into the integration by parts formula.
And that will give us the answer.
Well, it will transform the original integral into a new integral that's hopefully easier to solve. In this case, the new integral will be much simpler.
Okay.
It will be the integral of e to the power of x times dx.
And we know that's just e to the power of x.
Exactly. So we were able to solve the integral using this formula.
Wow, that's pretty cool. But how about a different example? Something a little harder.
Okay, let's try the integral of the natural log of x. What do you think?
Okay, that sounds tricky. How would we even start with that one?
Well, it looks like there's only one function, but we can actually think of it as the natural log of x times 1.
Oh, I see. So we can still apply LIATE.
Exactly. So we choose the natural log of x as u.
Because it's logarithmic.
Right. And we'll choose 1 times dx as our dv.
Okay, I'm with you.
Then we just differentiate u to get 1 over x times dx and integrate dv to get x.
Got it. And then we apply the formula again.
Yeah, we plug it all into the integration by parts formula and simplify. And in this case, we end up with the integral of 1 dx.
Which is just x.
Exactly. It simplifies really nicely.
So we were able to solve two pretty complex integrals using integration by parts. That's really impressive. Is there anything else we should know about this technique?
Well, there's a lot more we could talk about. For example, sometimes you have to use integration by parts more than once to solve a single integral.
Really? More than once? That sounds complicated.
Yeah, it can get a bit tricky, but it's the same basic idea. Like, let's say we have x squared times e to the power of x.
Right.
So we'd choose x squared as u and e to the power of x dx as dv, just like before.
Right.
But then when you differentiate u and integrate dv, the new integral you get, it still has a product of functions.
You have to use integration by parts again.
Exactly. You keep going until you get an integral that you can solve directly.
Wow, so it's like a chain reaction.
It is. You're basically breaking it down step by step. But don't worry, there are ways to make it easier to keep track of everything. Like there's a method called tabular integration.
Tabular integration, what's that?
It's basically a way to organize the steps when you're doing multiple integrations by parts. It helps you keep track of all the derivatives and integrals.
Okay, so that can be helpful when things get really messy.
Yeah.
So all of this is cool and all, but when would you actually use integration by parts in real life?
Oh, it comes up in a lot of different fields, actually, like physics, for example.
Oh, really? Like how?
Well, imagine you have a spring. And you're trying to calculate the work done as it stretches or compresses.
Okay.
The force the spring exerts, it changes as it stretches. It's not constant. So you have to use integration to find the total work.
You'd use integration by parts for that.
A lot of times, yep. And it's not just physics either. It's used in electrical engineering too.
Interesting. I wouldn't have thought of that. What would you use it for in electrical engineering?
Well, you can use it to analyze circuits, like circuits that have components that store and release energy over time. Their behavior can be modeled using integrals, and we can use integration by parts to solve those integrals.
So you can see how the circuit behaves over time.
Exactly. And you can use it in economics and finance too, believe it or not.
Wow. So it's really all over the place.
It really is. It can help model things like income streams or the present value of future cash flows. It's a pretty versatile technique.
Yeah, I'm seeing that you mentioned before that it's connected to Fourier and Laplace transforms.
That's right. Fourier and Laplace transforms are these powerful tools for analyzing signals and systems.
What do they do?
Basically, they break down complex functions into simpler components, kind of like taking something apart to see how it works.
And how does integration by parts come in?
Well, the formulas for these transforms, they involve integrals, and you often need integration by parts to solve them.
I see. So it's like a bridge between these different concepts.
Yeah, that's a great way to put it. It links these different mathematical ideas together, which is super important in fields like signal processing and electrical engineering.
Well, this has been a fascinating look into integration by parts.
Mm.
It's clearly much more than just a formula. Like you said, it has all these connections to different fields and applications.
It really does. It's a testament to the elegance and practicality of calculus.
Definitely. So before we move on, is there anything else you think our listeners should know about mastering integration by parts?
Well, the best way to really get good at integration by parts is practice.
Yeah, practice makes perfect, right? What's the best way to go about practicing?
You can start by working through problems from textbooks or, online resources. There's tons of stuff out there.
So just jump right in and start solving.
Yeah, but don't just try to get through as many as possible. Like, really try to understand why you're doing each step. Think about why you're choosing certain parts for U and dV.
So it's not just about memorizing the formula. It's about understanding how to apply it.
Exactly. And don't be afraid to try different things. Come up with your own integrals to solve or find problems from different sources.
So kind of mix it up a bit.
Yeah, the more you vary your practice, the better you'll get at recognizing patterns. You'll start to see when integration by parts is the right tool to use.
That makes sense. So we can make our own problems. That's cool. Is there anything else we could do to help us get better at this?
Well, you don't have to practice alone, like study with friends or classmates.
Oh yeah, that's always a good idea.
Yeah, you can work through problems together and talk about different approaches. Sometimes explaining something to someone else can help you understand it better too.
That's true. Sometimes I don't realize I don't understand something until I try to teach it to someone else.
Right, exactly. And don't forget, there's always help available if you need it. Like your teachers or professors or even online communities. There's tons of resources out there.
It's good to be reminded that we're not alone in this.
We're all in this together, right? The more we help each other learn, the better we all do.
That's a great point. Well, we've covered a lot of ground today, from the basics of integration by parts to real-world applications. We even touched on some of the bigger picture ideas like problem solving and the connections between different areas of math.
Yeah, it's been a great discussion. Hopefully our listeners are feeling a little more confident about using integration by parts now, even if they encounter those really tricky integrals.
I'm sure they are.
Yeah.
Well, it's been a pleasure chatting with you today. Thanks for joining us and sharing your expertise.
It was my pleasure. I always love talking about calculus, especially integration by parts. It's such a cool technique.
It is. Well, thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.